All right, welcome everybody. This is New England Dynamics and Number Theory seminar again. And I think this is the first time this semester when we have a speaker from New England. Indeed, we're happy to have Ian Hoover from Boston College. And his title we now can see in broad daylight with very nice coloring scheme. Effective equidistribution on Hilbert modular surfaces with an application to counting quadratic forms of squared discriminant. Welcome, Ian.
Hi, thank you for having me. So, I'm going to be talking about effective equidistribution on Hilbert modular surfaces. To begin, I'll go over the preliminaries of the objects we're looking at, talk about what my result is that is somewhat new, and then how it's applied to counting certain types of quadratic forms. And if there's time, we can also talk about some of the proof strategy involved. So without further ado, I'll just jump right in. So obviously, we're probably all familiar with this, but just recall our matrices in SL2R act as isometries of the hyperbolic plane, and we can associate the matrix to where it takes I under this fractional linear transformation, and this gives us an association between the group mod K or SO2 and the upper and hyperbolic space itself. And here we just have a picture of the lattice given by SL2Z acting on upper half space, a model of the plane. Now, Hilbert modular surfaces are essentially a generalization of this idea to lattices inside acting on products of hyperbolic planes. So they're generated by number rings, so real number rings. So for us, let's take a real number ring L of degree n. And so by real, just recall that this means that all of its embeddings into Q are actually embeddings into R. And if we fix some order of those embeddings into R, so we'll just fix that for all time as far as we're concerned, we get an embedding from the ring of integers into the product of R, so into Rn, and it embeds as a lattice. Of course, the norm of an element in our number ring is the product of all these different embeddings. And the units, so what is unique about these real number rings, right, is that their units form a free rank n-1 Z module. So let's look at a specific example here. So what we have pictured on the left is a quadratic extension of Q. I believe it's Q adjoin root 2. So the integers of that extension. I've done exactly the embedding I've outlined. So the x coordinate is one embedding, the y coordinate is the other embedding. And then our units are the elements whose products of x and y coordinates are 1 or -1. So the units lie along this unit hyperboloid, if you will. And the fact that the units form a free rank n-1 Z module is just saying that there's one unit, one fundamental unit, and all the other units in the ring are simply powers of this unit. Now, on the right, what we have is a picture of this number ring if we take the log of the absolute value of all the coordinates here. And the reason we do that, the reason I'm showing you this picture is so that the action of the units on the numbering itself is somewhat clear. So here, there's an obvious periodicity along this off diagonal of the line y equals -x, and that corresponds to multiplication by this unit. So in the log space, multiplying by a unit is just shifting in a direction that's orthogonal to the line y equals x. And so the fundamental domain of the action of the unit gives us this this strip that's finite in one direction and then infinitely long in this other direction. And the reason I'm showing this is because it helps build intuition for sort of the shape of the diagonal matrices, mod the units, the action of the unit. So this way we've dealt with the real extension of Q. We can also deal with the matrices of determinant 1 over this number ring. So we can
Can I ask
embed.
a quick question?
Yeah, absolutely, absolutely.
About the previous slide. So
Yep.
Can you understand the units lying inside the ring of integers? Is the fact that it's free rank n-1 z module geometrically as some like condition on the codimension as in that picture? So like it seems as if you have like a codimension 1.
Yeah, you know, exactly. So the proof sort of follows from the picture on the right of this fact, which is that your unit. So the middle of this blue strip, right? The middle of the blue strip would be the line y equals x, and that corresponds to elements whose magnitude of their embeddings are all the same. So for a quadratic extension, right, that's your actual just real integers, right? They don't change embedding. Or if you, or the element sort of, oops, sorry, I don't know how I did that. The element root 2, for example, would be embedded as root 2 or minus root 2. And so when you take the absolute value in the logarithm, the x and y components are the same as well. So it's like, that also lies along this diagonal y equals x. Now units are going to be perpendicular once you take the logarithm. They're going to lie in this perpendicular space. So they're going to be, once you take the logarithm, they're going to be perpendicular to this line y equals x. And that space has a rank. So it's basically they lie in a hyperplane that's perpendicular to the vector 1, 1, 1, 1, 1 for as many ones as you have as n, right? Does that make sense?
Yeah, thank you. Yeah, thanks.
Yep. So we can do the same thing with the group called the Hilbert Modular group, SL2 of our number ring. We embed it as a lattice inside SL2R to the n. And just some facts. Some of these are elementary. Some of these are less elementary. Our units give us non-trivial diagonal matrices, right? By definition, they have inverses. So you can make a diagonal matrix inside SL2OL with your units. And while this is a very specific set of possible lattices inside SL2R to the n, it turns out in some sense, these cover the irreducible lattices inside SL2R to the n. So if you have an irreducible lattice, it's going to be commensurate with some Hilbert modular group, basically. So, and the quotient space you get captures some of the number theoretic properties of the ring. So our cusps correspond to the ideal classes of the ring. And as with SL2Z, our Hilbert modular group acts on the product of upper half planes, simply each coordinate acting on its respective coordinate. And so we get a homogeneous space just as before. And we have a finite volume fundamental domain. Is there a question? And so this is what we would call our Hilbert modular surface, or also called a Hilbert modular variety, I believe. And what I'm going to be looking at is dynamics on these spaces. So just to make things a little more explicit, we can look at the Iwasawa decomposition. So we write elements as a product of unipotent, a diagonal, and an element of SO2, and we just do that in each coordinate. And then we have, our Haar measures on each of these subgroups. And when we do this, we look our associated point in our homogeneous space is simply the real component corresponds to the unipotent element, and the imaginary component corresponds to the diagonal element. And because we're not looking at the unit tangent bundle, right, the SO2 part doesn't really show up. Now, I want to look at the action of the diagonal component on, so our group A has a non-trivial intersection with our lattice gamma mod L, and just as in for the numbering, this action comes from the units. And so for just looking at the two-dimensional case, you would have, so this would be a quadratic extension, you'd have a single unit that you can multiply the unit and its inverse in each parameter. So if you have y1 and y2, you could multiply and divide y1 and y2 by the same thing. And this is what the action of the unit diagonal matrices would give you. And so the fundamental domain of that would look like this cone here in blue. And it's convenient often to redo your coordinates so that we look at the product of y1 and y2 as one coordinate, and then essentially the difference of their logarithms as the other coordinates. This is how it works for the two-dimensional case. And then our fundamental domain of the units acting on all the diagonal matrices looks like, again, it looks like a strip that has one dimension where it's infinitely long, and then the other dimension, all the other dimensions are going to be finite. And if you normalize properly, right, it's just going to be between -1/2 and 1/2. So like an interval square in one direction that's then infinite in the final dimension. And so this is what sort of the diagonal orbit looks like in this group. And well, so due to Efrot, we have the definition of the Eisenstein series, and we have a whole family of Eisenstein series, but importantly, it's only one complex parameter, S, and that corresponds to the fact that we only have sort of one infinite direction now once we've modded out by our lattice in the diagonal group. All right. So moving on. So let's just, what are the dynamics we're looking at? Well, just let's recall the definition of the two important dynamical ideas, right? So mixing is if by the action of the group, the integral of a product would become just the product of integrals, and if this were effective, it would mean that we'd have some explicit error term in terms of our functions and as a function of our group element that we're translating by. And equidistribution is a similar idea, except you're instead of integrating over space, you're integrating over some subgroup orbit on that space. And we could look at a single function, and it equidistributes if, as we translate this orbit by some element of g, it turns into just the integral of the function over the quotient space plus some effective error term. And I've ignored the need to normalize often in some way, but this is the idea. And for what I'm going to consider is so we're going to integrate over the diagonal orbit. So integrating over A mod gamma, and then translating that orbit. So what that looks like is, so just for compactness, we'll write A sub gamma to mean the diagonal group quotiented by its intersection with the lattice. And we're going to look at a K invariant test function. And then when we translate by an element of the group, if we use our Iwasawa decomposition coordinates via a change in variable a times some other a, we can just ignore that, where it's a k invariant test function. So in the end, all we need to really consider is when we're translating by an element of n, our unipotent group. And in explicit coordinates, what happens is, so a sub y translated by n sub t is going to look like this. In each component, you're going to have your real part is t, y, and your imaginary part is just y. So in the n equals 1 case, what that looks like, your diagonal orbit would simply be of, say, the point I, would be the vertical line. And then as you translate it, it simply shears that line to the right. And so this is just a picture on SL2Z of this situation. So if in the n equals 1 case, a mod gamma is just a. As you shear it, it moves to the right, and we see it's inside this fundamental domain. It looks like this red line that's wrapping around. And so in general, much more general than what I'm considering here, there's effective results for mixing properties, also, aka decay of matrix coefficients. And this sort of equidistribution is known also to be true, but not effectively in more general cases that I'm considering. And there are effective equidistribution results for the translates of finite volume orbits. And more recently, there is effective results for translates of infinite volume orbits, but as far as I'm aware, only for the n equals 1 case. So that would correspond to the picture that we have here on the bottom right. This is the n equals 1 case, where the Hilbert modular group in that case is only SL2Z. Of course, it was more general than that. They also have for thin, gamma being thin, and other lattices as well. But so the new result that I'm presenting today is that we have an effective result for diagonal group orbits for arbitrary n now. So gamma mod sub L mod H to the n. So what that looks like is for a psi suitable k-invariant test function, there's some explicit constant eta that sort of derives from the results for effective mixing. And as we integrate over this translated orbit, it approaches the mu of psi is just the integral of psi over the quotient space. And then we have scaling factors and then our error terms. And some key distinctions between this and the one-dimensional case, the n equals 1 case, is that, well, we have n shearing parameters or n translation parameters. So the t sub j. And we don't get unconditional equidistribution for if our translation element is just leaving any compact set. And in fact, if some of the tj's are going to 0, it actually messes with the equidistribution result. It's just sort of an unfortunate consequence of the strategy. And it doesn't show that there isn't equidistribution in that case, but it also sort of fails to show equidistribution as well. So
excuse me, so
yes.
So you have, so gamma L, so this quotient is the translated sheared this copy of the diagonal subgroup, and there is no dependence on L, so you translate by L.
R and D are both properties of L.
Oh, they're okay.
So R is the
right.
regulator of the cusp at infinity, which is a property of the number ring, and D
So
is the discriminant.
So the main term depends, but not the error term.
You're right.
Okay.
Well, so I think there might, some of the implied constants in this error term will depend on L. And of course, it depends on psi as well, and a bunch of, Sobolev style norms on psi. So there is the sort of the opportunity in the higher dimensional case to consider partial orbits, and I illustrate with a picture. So in the two-dimensional case, the A sub L was this strip that we were translating, and it has one infinite direction and one finite direction. And if we have a function that's constant on y naught, which is the vertical direction, and just some other function on the horizontal direction, so one way to think about it, so the obvious case would just be some indicator function of some subset of the interval. So instead of the interval times the positive real line, you could have some subset of the interval. And this would be what we might call a partial orbit, a partial diagonal orbit, because you're not integrating over the whole diagonal subgroup anymore, or mod L. You're not even doing that, and you can still equidistribute. And then the main terms are all the same, and your error term now will involve norms that now involve this, whatever your function phi is. So it involves the total variation of phi as well as its L2 norm on the in the perpendicular hyperplane to y naught. So this is sort of a type of orbit that is made possible by looking at higher dimensions, and so that also equidistributes. So then the next part is to look at counting quadratic forms, and I just want to sort of briefly go over the case where we're looking at integer quadratic forms, because looking at quadratic forms over these real numberings is very analogous, but it's a little more confusing to talk about. So let's just talk about the integer cases first. So if we have an integer quadratic form, we can think of it as an integer triple, and if it has a specific discriminant, then it's going to lie on this quadratic surface, this three-dimension, this variety. So the integer quadratic forms of that discriminant correspond to the integer points of this variety. And then what one might want to know is how many of those forms lie within some Euclidean distance r of the origin. And this is a very sort of classic problem of counting integer points on varieties that there's been a lot of work in. And so how does this kind of equidistribution result help us count these quadratic forms? Well, it comes down to the way that SL2Z matrices give us congruent forms via coordinate changes. So for a gamma in SL2Z, we can transform one form into another form that we'd call congruent simply by this action of multiplying by the transpose on one side and the matrix on the other. And for a given discriminant, we can partition the set of all integer quadratic forms of that discriminant into the SL2Z orbits of those forms. And it's sort of an elementary fact that there's going to be a finite number of different orbits then so what we do is for a given quadratic form. So yes, of course.
Perhaps I'm remembering this incorrectly, but is that related to the fact that you have like finally many forms of like particular genus?
Well, of course, the number of orbits is precisely I believe it's related to the class number of the quadratic extension of like Z Q adjoin the square root of the discriminant. So this it's.
But does this have any relation to like the genus of the quadratic form or no?
I'm actually not sure. Maybe somebody else can.
Okay. Okay.
I don't know if it does.
Maybe I was misremembering.
But so how this is related to the dynamical problem is that, so a given norm, a given quadratic form, if we fix a quadratic form, then we can associate the norm that we get and given a matrix in SL2R, or SL2, yeah, SL2R, when we conjugate this form by that matrix, it gives us a new form, and we can use that, the Euclidean norm of that form to give us a norm of the matrix. The norm has to be in quotations now, as it's not really, it doesn't satisfy the axioms that you normally associate to a norm on our set of matrices. But what you can show is that the normal Euclidean metric on triples that are our forms is a k-invariant function on our matrices. So we can, instead of, for a matrix ay and x k theta, its norm is just going to be the same as ay and x. And then we can view our norm ball as elements of our as a set inside of our homogeneous space. So this corresponds to now matrices that live inside this set. And then we can count for a specific, for each congruence class. So if we pick a V inside an element representative of each congruence class of quadratic forms, we can then count the number of matrices that lie inside this norm ball R on our homogeneous space, which correspond to the lattice points of our SL2Z action. Now, what that looked like is there's sort of three different possibilities, which depends on the stabilizer of the form that we're looking at. So if H is conjugate to A, it's the stabilizer is conjugate to that diagonal group, we get these shears. So then the boundary looks like the shears that we were talking about. The other situations correspond to horocycles or spheres. And for a given discriminant, there are, well, first of all, there's finitely many classes of integer forms, but each class will have the same conjugacy type of the stabilizer. So the different classes of form, so for a given discriminant, the different classes of forms, they're going to have conjugate stabilizers. So sort of you only one of these pictures will apply. And if the discriminant is a square, then it's exactly the H is conjugate to A situation that we have. And so now for the SL2Z case, this has all been resolved. And so the boundaries of these sets corresponds to the H orbit, and for the diagonal orbit is when we have a square discriminant. And this is a case that was resolved somewhat recently. Kelmer and Kontorovich, 2017, they counted this by proving the equidistribution of this one-dimensional translate. They then got accounting results for quadratic forms of square discriminant. And now this is maybe a opportunity to see this equidistribution in action just for our entertainment. Give me a second. I just need to share a screen. All right, so what we see here is the blue. The blue corresponds to our translate, and the red corresponds to viewing it inside the fundamental domain. So this is looking at SL2C, and then we're shearing or translating. And as we translate, we can see it folding back inside of the fundamental domain. And what equidistribution tells us is that as we continue, the overall density will start to mimic the hyperbolic density on the space, right? And it definitely looks, I'm sorry, I don't don't know why I did that. There we go. This is done by using sort of transparency, so that the more overlap you have, the darker the color, the less overlap, the fainter it is. And the original distribution corresponds to the Haar measure of the group A that is generating the orbit. That's how we get the picture. All right, so I just wanted to share that with you guys before returning.
The overall idea is that when we like iterate this process over and over, we're supposed to be getting like, roughly speaking, the Haar measure of this fundamental domain. Or?
Yeah, exactly. So you start out, well, so you just have a shear parameter t that corresponds to the slope of this line, right? As t goes to infinity, the slope of this line goes to 0. And when we put it back in, when we fold it, when we represent it as all living inside this one fundamental domain, points that are evenly distributed along the sheared line, so points that are evenly distributed along this blue line, when I say evenly distributed, I mean with respect to the Haar measure of the diagonal group, they end up being evenly distributed inside this fundamental domain with respect to the hyperbolic measure.
Oh, okay, thank you.
Which corresponds to the Haar measure of SL2 R, right?
Yeah.
Okay, but in this picture you have two parameters. You have this angle, or the shearing parameter, and the length of the line segment that you are rotating.
So this is a good.
You can.
There's a good point. The line segment is not infinite, but that's only because I'm only including what I need to include to show what happens in this.
So it's actually infinite.
It could be infinite, right? But I just didn't want to ask the computer to draw an infinite line.
But then you you integrate from 0 to infinity and then you move, or is it two-parameter problem somehow?
Well, so so you only need, so it turns out, right, you only need to integrate from a phi. So you have what we would call, we have the involutional symmetry of the situation. So what's outside the unit circle corresponds to what's inside the unit circle.
That's right. Right.
So we don't need to look at the full integral from 0 to infinity. We can look at the integral just from the edge of the circle to infinity.
Yes, but it's still,
and it's going to be mirrored.
It's still of infinite length.
Yes. I mean, I only drew this line to what needed to show up in this picture, right? So if you were to scroll up past the top of this image, the diagonal lines would cut out eventually.
Okay. All right. Fine. Thank you.
Right. Yeah. And then the bit below inside the unit circle is just the involution of that finite line. So that's why it doesn't actually go all the way to 0. But anyway, so all right, I need to stop sharing. Let's go back to the presentation. And so the idea is to do the same thing with now counting forms over numberings. So if our coefficients now belong to a numbering, and we want our stabilizer to be conjugate to A, that corresponds again to this forms with square discriminant, and then when we view it as a point on a variety, we would view it as a point on this R to the inside R to the 3n, and we look at each triple, and then we have sort of the n possible discriminants corresponding to each possible embedding of this triple. And what we want to count is, again, how many forms for this discriminant fall within distance R of the origin. But now, right, our distance now takes into account every possible of the n embeddings. And now, in general, the number of forms, the number of congruence classes of forms is mysterious, but for a square discriminant, we can actually compute this all quite explicitly. And then we can express our region again explicitly for a specific stabilizer. So sorry, for a specific representative O eta O is 0 eta 0. So then the stabilizer is precisely A. We can compute the region that corresponds to forms of norm less than R. And because the A action, because A intersects the lattice somewhat non-trivially now, the lattice points themselves don't directly correspond to quadratic forms or unique quadratic forms, but we look at equivalence classes of lattice points modded out by the action of the units, essentially. But what we get is essentially a very analogous picture where we have sort of a product of the cones that we had before. We have these cones, and now we sort of have a product of those cones where the slopes have to, the sum of the squares of those slopes lie within essentially a circle, or I mean, it's going to be an ellipsoid depending on what exactly our discriminant is. So essentially the equidistribution result I showed at the beginning gives us somewhat for free accounting of the number of forms in the orbit of this specific form. For the other congruency classes, it turns out the picture is basically the same. The stabilizer is no longer specifically the diagonal group. You have this other term, but we can show that the way it intersects the lattice is going to be the same. It's going to be a rank n-1 free multiplicative free Z module. And instead of generated by the units, it would be generated by some power of the unit. So what essentially happens is that you, instead of a cusp, you're looking at a slightly wider cusp, potentially. And in hypothetically, if you wanted to know specifically what that new width was, you could compute it. If you had a specific discriminant and a specific number ring in mind, you could then compute what this new width was, and it affects the sort of scaling parameters on the main term of the equidistribution, but nothing else really. So then we can use our equidistribution result and sum over the counting on each of these conjugacy classes of form, or congruency classes of forms, and we get our counting result. So the number of forms of norm less than R of discriminant D, as we have an explicit result here, and then our constants are of course dependent on D. Yeah, so this is just an application of the equidistribution result. All right, so it looks like we still have some time left, I think. So we can talk a little bit about the proof strategy, and this largely follows from this largely follows this strategy of Kelmer and Kontorovich's work for the n=1 case. So we use the involutional symmetry that I was talking about before, so we are not actually integrating over the full diagonal orbit. And we take our test function and to split it into two parts. So we look at the part that's invariant under the action of the unimodular group, and then everything else. And we use what we call decay of Fourier coefficients to show that this remainder part essentially goes to 0, and that is what gives us the error term of the equidistribution. Sorry, I didn't mean to click. And then the part that's n invariant is what is shown to approach the integral of the function over the whole space, and then use properties of Eisenstein series to show that equidistribution for the n-invariant part. So the involutional symmetry, in our case, corresponds to, instead of integrating over this full strip, we can integrate over sort of half of this infinite strip. So it's infinite now only in one direction, only in one, instead of going from 0 to infinity, it's going from something finite to infinity. And then when we split our function psi, it's essentially the action of n. It gives us periodicity in the real component. If we look at our function as a function on this upper half space, or product of upper half spaces, we have this real part and the imaginary part, and the unimodular group acts by translation on the real part. And so the lattice gives us periodicity in the real parts, which then can be used to create a Fourier expansion of our test function, whose Fourier coefficients are functions of the imaginary parts, right? And so in the n=1 case, this is a one-dimensional Fourier series. In the for general n case, we have an n-dimensional Fourier series. And I'm using stars here to indicate elements of the dual lattice to the number ring. Right? But it's the same idea. So then you can look at the function of non-zero that correspond to the non-zero elements of the dual lattice, and that corresponds to the part of the function that's not invariant under translation in the real coordinates. And then what you're left with is simply the 0th Fourier coefficient, which just corresponds to the integration of the function over the action of the unimodular group mod the lattice. So now we might be getting a little into explicit details, but I just wanted to show where this problem with some of the translation parameters going to 0 comes from. So a key step is to show this decay of Fourier coefficients. So for a given Fourier coefficient, for a given element of the dual lattice, its associated Fourier coefficient will go to 0 in this explicit way as the y's go to 0, right? As the imaginary parts go to 0. And a step of this process is to approximate our sheared space by sort of assuming that the imaginary part is locally constant, and you can sort of right. So when we do this, and you assume that the imaginary part is locally constant, and then you get an error term from that assumption. And if we divide our region into smaller regions and sum over these regions. But the point is that we end up looking at this this integral here, where we have an integral over a small space of this exponential term. And it's important to be able to bound this using the fact that this is oscillating. And if so, A star is an element of the dual lattice, and if in general we can't really say that as A star leaves compact sets of near the origin that every component gets large. All we can say is that some components necessarily get large, and so to guarantee like some kind of oscillatory nature and then cancellation here, you need to be able to use the fact that we know that some component of A star is large and it's going to be multiplied by something non-zero. So if some component of T is 0, it's much harder to use this oscillation because you don't necessarily know which components of A star are large and which components are close to 0. And so if the components that are large correspond also to where T, the component of T is 0, then you don't get that oscillation. And then the error term is not cannot be bounded as easily. So that's where the sort of the error term ends up blowing up, right? Or that's why the error term ends up blowing up when you have components of your translation parameter that are near 0. This is from this part here. The Eisenstein series part is very similar to the previous work. You look at your folding and unfolding, so you can express the inner product of a function with Eisenstein series as an integration over the domain of the stabilizer of infinity acting on our space H sub n. And then what happens is, so we're looking at so we used involutional symmetry to only look at a partial orbit in the y0 direction, and that, right, it ends up being multiplied by y0 s. So you can sort of, the fact that we're not integrating over all of y0 can be, what that comes out as is kind of the Moline transform of the indicator function of this y0 part. So going from 0 to then 1 after y0 is above a certain value. And then for this function in the y1 direction, if we're restricting to some indicator function there, what comes out is we have this for the other Eisenstein series. So for m in z to the n minus 1, we end up with the Fourier transform, or the Fourier series corresponding to our phi function, which is what we restricted the orbit in the y1 direction. So there's this. So in the higher order case, now as opposed to just the n equals 1 case, we now have the Fourier series corresponding to the function on y1, y2, etc. Whereas before we only had sort of the Moline transform associated with the vertical part, the infinite part.
Can I ask a question?
Yeah, absolutely.
So in your result that you stated earlier, you had this, like, on the equidistribution result, you had some like algebraic number theory information. So you had the regulator at the cusp at infinity,
Yeah.
and then you also had this discriminant. So do these come in your formula from your analysis of Eisenstein series?
Yes, exactly. So that's a perfect question, because so when you do this, right, you end up you have to deal with the residues of these things at s equals 1, and the geometric information about, sort of the algebraic information about L comes from the residue of this 0th Eisenstein series. So this one specifically. The other ones don't give you residues, and so they don't really contribute to the main term. Yeah, exactly. So it comes from that. So the equidistribution comes from exactly that.
Oh yeah, it's very interesting. I didn't know how that would come up. It's cool.
Yeah. It is pretty cool. And then that's from, and the facts about the Eisenstein series are from the work of Efrot, and I believe it was 78. So I think this might be a good opportunity to, so there's some more, but I think this might be a good opportunity to stop if I don't know how much time I have left.
Well, officially we can run until 1:30, but it's up to you. You can take a break now, and then maybe there will be questions.
All right. Yes. Let's continue if there's no questions then. So the next piece of the presentation is showing sort of talking a bit about how we use equidistribution to count, which I think probably a lot of us are some of us are more familiar with than others, but the main idea is almost classical. And here I'm quoting the theorem of Eskin and McMillan, but also we have the work of Duke, Rudnick, Sarnak, and others. I think that it follows a similar idea. The main idea is that if you have a sequence of growing sets that are nearly invariant under the small neighborhood of the identity, and when you say nearly invariant, you need for if your Bn are not of finite volume, you need to phrase it slightly differently. But because of that, you can count a smoothed function instead of the hard counting function. And then to use equidistribution to integrate over this set B sub t, we can sort of foliate it by the boundaries of all the smaller sets and integrate over those boundaries. And then the equidistribution of those boundaries gives us our counting result, essentially. There is one almost pitfall in all this is that for the higher for n greater than 1, our sets look like some kind of ellipsoids, and the boundaries were these circles where our shearing parameters, the sum of the squares for our shearing parameters equaled some constant. And so when we integrate over this, we have to integrate over those places where we don't have equidistribution, right? Rather say where we can't, where I am not able to show equidistribution. So where the error all along these, where this circle intersects the axis, will go to infinity, right? So we have these like poles, and fortunately, this was not actually a pitfall. It was just an almost pitfall because the rate was such that we still get that the error term goes to 0 even despite integrating over these asymptotes at these places where it intersects the axis. Yeah, I think that's it, except to say thank you, and obviously huge thanks to Dewey Kelmer, who has helped me immensely with every stage of this research project. Yeah, I guess I'll see if anyone has questions.
Okay, well, let's first thank the speaker, maybe like this, by unmuting ourselves. And then it's question time, questions, comments. Anybody?
I have a question that you stated, but I just want to make sure that I understand. So if the two shearing parameters, if one of them is actually 0, it's over in the two-dimensional case,
Yeah.
if one shearing parameter is 0 and the other one goes to infinity, then the method doesn't give equidistribution even?
Yes, if one of them stays at 0, yeah.
Yeah. Okay.
And it's not, so this is definitely something for further work, right? It's not clear yet if equidistribution fails, so maybe we don't have polynomial error rate, or if we just need a cleverer method. It's unclear which of those cases it is, but fortunately it didn't affect really the counting result, despite having that sort of limitation. That's a good question.
I saw that you skipped one slide, one of the slides you didn't talk about that had this the Gauss circle problem. Could you maybe talk about that? Or
yeah, I guess so I sort of started to doubt myself, I guess, but it was just that to show how we can use equidistribution in a very sort of explicit setting to count lattice points, and the process of using a smooth counting function. So if we want to count lattice points inside of a set, right? The one way you could do it is put a delta function at every lattice point, and then integrate over the indicator function of your set, right? And that'll give you how many lattice points are inside the set. Now the idea is to, instead of like looking at it that way, is to periodize your set. So instead of looking at expanding one circle and counting how many points lie inside that circle, you could expand a circle around every lattice point and then count how many overlap at a single one. And that gives you the same thing, right? I mean, this bunch of nonsense on the left is just this picture on the right. And so instead of integrating over all space, you could look at, you could integrate over a single fundamental domain and look at the overlap. And then what you're integrating over, so you're integrating over this, you're integrating this function, which is, could be considered like foliated by circles, expanding circles, right? Up to a certain radius. And then we can integrate.
What do you mean by foliated?
Oh, just like if we have this disk, right, we can look at it, integrating over this disk, we could look at it as integrating over a circle of every radius. Right.
I got it, yeah. Okay.
And those are the boundaries of the set as it's expanding, right? So you're sort of integrating over all the different boundaries. And then because those boundaries equidistribute, that tells you what, you can use that to calculate the integral you get in the end. The issue, right, with using delta functions is that your error terms from your equidistribution involve Sobolev norms, which are not defined for a delta function, which is why we need to use some kind of smoothed delta function instead, which introduces its own error. But this is something you quantify and incorporate, right? So that's just sort of the, you can then apply this to the same idea to the situation of counting lattice points of SL2Z or SL2OL as we did. So it's the same sort of process.
Right. Other comments, questions? Well, that's.
I have a.
Go ahead.
It's not a question. It's just a remark about the initial question about the number of a quadratic form of a given discriminant. Mm-hmm. I'm not completely sure, but I think it should equal the sum of the class numbers of all overorders of the order of discriminant D. I'm not completely sure, but it should be correct. Something.
Because I remember there's something like this in the book of Cox on like primes of the form x squared plus ny squared. It's like in one of the beginning sections. I read this a while back, but I don't remember the details.
Because you have to count the fractional ideals up to linear equivalence, but not just the fractional ideals belonging to the order of discriminant D, but of all overorders. More or less, the correspondence has to go this way. Okay, it was just a remark.
Yeah, thank you. That's a good contribution. Yeah, thank you very much.
Okay, well, it's 1:15, so let's thank Ian again for a great presentation. And we're almost done with the semester. We have just one more talk next Thursday. So I hope to see many of you there.